we'll we have Sümeyra Sakallı as our guest at Üçgen from University of Arkansas, and she will tell us about symplectic 4-manifolds. Please go ahead, Sümeyra.
Thank you very much again for your invitation. It's a great pleasure to give a talk in your seminar. And actually, I'm doing low-dimensional and symplectic topology, but my research is also related to algebraic geometry. I mean, I'm mostly interested in complex surfaces and configurations of complex curves or complex vibrations. And today I will try to give a brief overview about my research. And let me begin. First, I want to give the structure of my talk. At the beginning, I want to make a slow introduction. So I will define some basic notions. I will remind some facts about 4-manifolds. And these are all well known. And I will also give a brief history about exotic 4-manifold constructions, just to give a motivation for the subject. And second and third parts are about our constructions of exotic 4-manifolds. They are both coming from pencils of complex curves of small genus. And actually the last one is the one that I promised in my abstract, but then I also decided to talk about this one. It is also related to algebraic geometry, and I wanted to also talk about that. So it is a bit different. Sorry about this. And let's begin. First of all, when I say small manifold, it means a manifold whose Euler characteristic is small. And exotic manifolds are smooth ones. These are homeomorphic but not diffeomorphic to each other. So topologically, these are the same manifolds, but their smooth structures are different. Then we call them exotic. And I'm studying in dimension 4 mostly. And this dimension is a bit different than other dimensions. And I want to mention what is different, what is interesting with this dimension. And these are all well-known facts. Let's remember them. If you look at first open manifolds, open means that these are non-compact without boundary. And if the dimension is different than 4, then there is no exotic Rn. So it is the n-dimensional real vector space, which is also an open manifold. And if the dimension is different than 4, each Rn admits a unique smooth structure up to isotopy. So in other dimensions, there is no such thing called exoticness. However, if the dimension is 4, then in fact there are uncountably many exotic copies of R4. And in fact, at first Friedman showed that there is an exotic R4, then Gomf proved that there are countably many, and lastly Taubes showed that there are in fact uncountably many of them. And if you want to look at closed manifolds, and closed means that these are compact without boundary, for these, each closed n-dimensional manifold, again, if the dimension is different than 4, admits at most finitely many exotic copies. So in other dimensions, one can have at most finitely many. Actually, in dimensions 1, 2, and 3, there is again unique smooth structure. And if the dimension is higher than 4, then each of those manifolds can admit finitely many exotic copies. However, only in dimension 4, we know that there are many simply connected and closed 4-manifolds, and they have infinitely many exotic copies. And here I want to remark that this is an existential statement. We just say that there are many such manifolds, and all of them that we know have infinitely many exotic copies. But there are also some other special, let's say, closed 4-manifolds, and for those we don't know whether they admit an exotic structure or not. I will also talk about them in a second. But here I just wanted to emphasize the differences between dimension 4 and others. And in my talk, all of the manifolds will be smooth, closed, and oriented. And also, I'm working with more special class of manifolds. These are called symplectic manifolds. And here is a definition for any dimension. A symplectic manifold is given in this way. It is a smooth manifold M together with a closed non-degenerate differential 2 form omega. And from this definition, for instance, one can prove that all symplectic manifolds are even dimensional and they are all orientable. And let's go back to dimension 4 again. And we have a nice diagram. It shows us the relationship between different structures. And let's consider this outermost space as the world of closed topological 4-manifolds. And inside topological ones, we have more restrictive, more special class. These are closed smooth 4-manifolds, this smaller region. And inside smooth manifolds, we have almost complex ones. And sorry. Inside them, we have complex surfaces. These are complex 2, but real 4-dimensional manifolds. And we also have symplectic 4-manifolds. And complex surfaces and symplectic 4-manifolds have non-empty intersection. For instance, we have Kähler manifolds lying in this region.
Sümeyra, what is almost complex manifold?
Almost complex. It is a structure. The definition is a bit technical. Let me not go into that. It is just not intuitive, I would say. But yeah, it is lying between smooth and complex manifolds. Okay. So now I want to give a brief history of closed exotic 4-manifold constructions. And exoticness starts with Milner, as far as I know. And in dimension 7, he showed that there are 28 exotic 7-dimensional spheres. And I think this word exotic is due to Milner. It is his terminology. And first, he has done this work. And then in dimension 4, the first smooth, orientable, and exotic 4-manifold is due to Donaldson. And he showed that a special complex surface, these are called Dolgachev's surfaces. This surface is an exotic copy of a complex projective plane blown up at 9 points. And it was in 1987. And after Donaldson, many other constructions have been made. So exotic copies of smaller manifolds, like CP2 blown up at 8 points, going down to CP2 blown up at 3 points. These have been made by many people in many different ways. There is lots of papers and many different constructions via many different techniques. And here I try not to, list the names because there is always risk that, you can forget some names because these are a lot, but it would take 2 or 3 pages at least. But I just want to say that there are many different constructions. And let me mention just lots of the latest of them, the smallest of them. Exotic copy of CP2 blown up at 2 points. These are due to Ahmedov Park and then also Fintushel and Stern. And today, these are the smallest known exotic 4-manifolds. In fact, they have constructed infinitely many, as usual. And these are the smallest known 4-manifolds. And let me mention some open problems now. Let's first look at smooth category. We ask this question, do there exist exotic 4-dimensional sphere? And the conjectural version of this question says that there is no exotic 4-sphere, and it is called the smooth Poincare conjecture. So basically, it says that if you have a manifold which is homeomorphic to S4, then it must be diffeomorphic to that. And today, still we don't know the answer, whether it is true or not. And it is one of the major open problems in geometric topology, I would say. It is still open. And in the similar way, we can ask similar questions in the symplectic setting. Do there exist exotic CP2, complex projective plane, or complex projective plane blown up at 1 point? Or do there exist exotic S2 cross S2 product manifolds? And these are all open, and we don't know the answer. Or if you want to consider non-simply connected case, for instance, for torus, again, we don't know if it admits an exotic structure or not. And let me talk about this last question a little bit, S2 cross S2s. And the existence of exotic S2 cross S2 is open, but there is some progress in that direction. And first, let me introduce a notation. Let's say that n S2 cross S2 denote the connected sum of n copies of our manifold. So n is in fact B2 plus of the manifold. It is a contribution to the Euler characteristic, and it tells us how big or how small our manifold is. And last year we have proved this result. It is joined with Ahmedov and Park. We showed that there are infinitely many symplectic and also non-symplectic exotic copies of n S2 cross S2. Here n is an odd integer and n is at least 27. And here we want n to be odd because, as I said, it is the B2 plus of the manifold. And there is a formula, Noether's formula. And from that, we know that to have a symplectic structure, the B2 plus of the manifold must be odd. So we have this requirement here. And n is at least 27. And previously, this result was known for n is at least 175. So in the literature, there were much bigger examples, much bigger manifolds. In our work, we have made smaller constructions. Okay, and this year, after 1.5 years later than our work, now there is another recent preprint, and they proved the theorem for n is at least 23. And n is again odd, again to have a symplectic structure. So mainly they decrease the number by 2 factors. And by using similar ideas, similar approach. Okay. So how about exotic manifolds of this type? Let me introduce the notation if you like. So here we take n copies of CP2s, complex projective planes. And on the other side, we have CP2 bars. These are CP2 with reverse orientation. And we take m copies. And then we take connected sums of all of them. And then in general, we work with such type of manifolds. And as a remark, let me say that if you have such a manifold M, then when you add up the coefficients here, n and m, their addition is the second Betti number of your manifold. So it is the rank of the second homology. And their difference gives us the invariant, which is called signature. It is the signature of our manifold. So in fact, n is B2 plus and m is B2 minus, and you take their differences. And it gives us a topological invariant. We call it signature, sigma. And the formal definition of that is coming from the intersection form. But if we want to just look at this case, it is just simple. Just you take the difference of them. And here, let me mention one of our older results. It is joined with Ahmedov again. And let's say that M is a manifold of this type. Here, the coefficients are the same. So these are manifolds whose signature is equal to 0. And n is at least 12. Then we show that there are infinitely many exotic copies of such a manifold. These are all minimal. Minimal means that there is no -1 sphere inside our manifolds. So we cannot blow it down. We cannot get anything smaller. These are the smallest possible ones. And these are simply connected. And some of our manifolds admit symplectic structures and the others do not admit, but they are both smooth, of course. And these are all exotic copies of M. And previously, this result was known for higher values of n, for n is at least 25. And in our work, we have decreased that number by half. And on this same paper, we have another result. So let's say that M is one of the following 4 manifolds. The first group is manifolds whose signature is 1. And these are manifolds with signature is equal to 2. And the last group is manifolds with signature equals 3. And for each of them, and N is given in this way, for each of them, we again constructed infinitely many exotic copies of M. And previously, these results were known for higher values, as I wrote here. And in our work, we have made much smaller constructions. This is relatively older result, and I'm not gonna go into the details here. I just wanted to state, but if you are wondering, we can talk, of course. Now, in the rest of my talk, I want to talk about our other works. These are all about constructing exotic 4 manifolds via pencils of complex curves of small genus, and also via symplectic and smooth surgeries. And let me begin. The first one is, this is a joint work, and these are constructions via genus 2 pencils. And in this work, we have worked with a special type of surgery, and these are called generalized rational blowdown surgeries. These are due to Fintushal-Stern, and generalization is due to Park. And I want to give the main idea of this operation at first, and then I will be more precise. Let's say that you have a smooth 4-dimensional manifold X, and let's say that it contains a particular configuration of transversely intersecting 2 spheres. And let's say that we have CPQ. It is the closed neighborhood of this configuration. Basically, for each S2 in your configuration, you take S2 cross D2. You take their neighborhoods, and you get a smooth manifold out of it. And the boundary is a length space. It is a special 3 manifold. And then under certain conditions, you can take out that configuration, and then you can replace that with another 4 manifold having the same boundary. And when we do this replacement, we get another new smooth manifold. And this is the operation. So from X, we take out that configuration of spheres, and we replace that by another 4 manifold. It is called rational homology ball. Its homology groups with Q coefficients is the same as, homology groups of the 4 ball with Q coefficients. And as a result, we get such kind of manifold. It is what we call the generalized rational blowdown surgery. And of course, this CPQ is not arbitrary. Let me be more precise here. It is how we construct CPQ. So mainly we start with P and Q. These are relatively prime integers. And then we look at this ratio, P squared over PQ minus 1. And here we are taking the Hirzebruch-Jung continued fraction expansion. And when we take that expansion, we obtain these integers, Rk up to R1. And then we take their negatives, and according to those, we construct such a plumbing diagram. And let me now explain this configuration or this plumbing diagram. Here, each dot is a bundle. It is a disk bundle over the 2 sphere. And this dot is the other one. And when there's an edge between them, it means that these 2 bundles are plumbed together. It is a fiber to base identification. And these numbers, negative Rk minus 1, these are the Euler numbers of those bundles. And this is how we obtain CPQ. Or if you like, you can just consider the basis of your bundles. Just consider 2 spheres. So let's say that this dot is a 2 sphere, and this is another one. And when there's an edge, it means that they are transversely intersecting. And these numbers then, these are the self-intersections of your spheres. And then, as I said, you take its closed neighborhood, and it gives us a smooth four-manifold CPQ. And then, when you can find such a configuration, its boundary is a lens space given in this way. It is the result of Kesson and Herrer. And as I said, then you can replace that configuration with another four-manifold having certain properties, and you get another smooth four-manifold XPQ. I will skip other details, but I want to emphasize the last one here. Symington proved that she showed that this operation can be done symplectically. So if you start with a symplectic four-manifold X, and if all of your spheres are symplectic, then at the end you are getting a symplectic four-manifold. So this operation is not only smooth, but it can be done also symplectically. Okay. And let me discuss now one of our results. Let M be one of the following four-manifolds, either complex projective plane blown up at 7 or 6 points. Then for each of them, we constructed an exotic copy of M. Again, these are minimal, simply connected, and symplectic. And the main difference of our work is that we obtained them from a genus 2 fibration. So we have worked with a special genus 2 fibration, having two singular fibers of types 8.1 and 8.4. And we obtained these. And we also used other operations. One is what we introduced and used two spherical deformations, and then symplectic blow-ups and generalized rational blow-down surgery. By the way, blow-ups and blow-downs can be done symplectically. It is the result of McDuff, and we are using her result here. Okay, and I want to talk about the proof idea here, and I will give some details. And I want to introduce some notations at first. So Fn, n is a non-negative integer. These denote Hirzebruch surfaces. These are holomorphic S2 bundles over S2, having two holomorphic sections of self-intersections plus n and minus n. So these are complex surfaces having a nice bundle structure. And another notation, sigma g, as usual, it denotes a two-dimensional, compact and oriented and connected surface of genus G. And MCG of sigma G is the mapping class group of that surface. So it is the group of isotopy classes of orientation preserving diffeomorphisms of your surface. And it is also known that such a group is generated by Dane-Twists. On your surface, you consider standard simple closed curves, and the Dane-Twists gives us generators of that group. Okay. And moreover, in our work, we have worked with a special classification. These are due to Namikawa and Ueno. So they gave the geometric classification of all singular fibers in fibrations of genus 2 curves. So here, these are complex curves of genus 2, and they gave a complete list of all possible singularities. And more precisely, they consider such a family of curves. So these are fibrations, or family of curves, let's say. And the curves are complex, and their genus is 2. And here the base D is a small epsilon disk. And the total space X, it is a non-singular and minimal surface. And again, it doesn't have any -1 sphere inside. And our map pi is a smooth map over the punctured disk. So basically that means that for any point that you take on your punctured disk away from origin, upstairs we have a fiber, And that fiber is a Riemann surface. It is compact and non-singular genus 2 complex curve. And the restriction of your map to the punctured disk is a topological fiber bundle. And only over the origin there is one unique singular fiber. And they have worked with such a family, and then they gave the complete list of all possible configurations. And in our work, we have worked with two fibers coming from their list. So on the left, you see fiber, it is called type 8-4. So this one is a configuration of two spheres. So here each line is a complex line, or for us it is a two-dimensional sphere, and self-intersections are all -2. But here each irreducible component have different multiplicities, and only the first one has self-intersection -3. It is here. So basically it is a configuration of spheres. And on the right, we see another fiber. It is what they call type 8-1, and it is a 2-5 cusp. And I will also talk about that later. And so Monica and Ueno studied such kind of vibrations. This is the local picture. So they consider such complex curves, and these are over some small disk. But how about if we want to consider vibrations over CP1? Well, let's look at this case now. And I want to introduce a few more things here. First of all, we call a vibration relatively minimal if no fiber contains an exceptional curve. And it is called isotrivial if all smooth fibers are isomorphic to each other. And moreover, if you have such a vibration over two spheres, and it is in the complex setting, and this is a vibration of complex curves, and the genus of your fibers are at least 1, then it is known that such a vibration admits at least 2 singular fibers. So when you consider like the global picture, then you have to have at least 2 singular fibers. And in fact, Gonglu and Tan studied such kind of vibrations, and they showed that there exists relatively minimal and isotrivial vibration of complex curves of genus 2 over the two spheres, and they have exactly 2 singular fibers of types 8-4 and 8-1. So great. So they show that our fibers 8-4 and 8-1, they are coming together inside a complex surface S. It is an algebraic variety. But for us, it is just CP2 blown up at 13 points. And inside that 4-manifold, these 2 fibers are coming together. And then in our work, first we have found the number of sections and their interactions with the singular fibers. So let me go up. So I have these 2 singularities, and due to Gonglu and Tan, we know that they are lying inside an algebraic variety, or for us it is a 4-manifold. And later we figured out the sections, and in fact, let me try to draw. We found that there is one section hitting these 2 fibers like that. And when I say section, I mean a -1 sphere. Oops. It is just one section. And after showing the existence of that, then with a contraction morphism, we do successive contractions of -1 curves. Successively, we are, blowing them down. And as a result, we obtained a pencil. I am here now. So we show the existence of a pencil, and it lies in the second Hirzebra surface F2. So I'm on this side now, and I showed the existence of this pencil. And here C0 is the -2 sphere section, and F is the class of the fiber. It is another sphere. And I take them with certain multiplicities, and I consider their formal sum. And their formal sum is an element, is a member of a very ample linear system. And also, for instance, if you look at this B curve, this is an irreducible curve, and it is another member of that very ample linear system. And we also have this special tangency, the point P. And this is what I call, what it is called, a pencil of complex curves. And then we do blow-ups. We start this point P, and there is an algorithm, and it tells you how to proceed, when to stop. And according to that, I proceed, and I obtain the configuration on the right. And here, the red curve is the -1 section. And again, this black part, if you notice, this black part is the same as fiber of type 8-4 that I showed you above. And here, every component comes with different multiplicities, and they all match up, as in the Namikawa-Ueno list. I'm getting the exact configuration with the, correct self-intersections and correct multiplicities and stuff. And on the other hand, remember, we had this B curve here, and it is blown up many times. And in fact, it is a quartic blown up, how many? 13, 14 times. And by using a junction formula, you can show that this blue curve is a genus 2 curve, in fact. So it is just a generic fiber of the fibration. And great, so I have reconstructed one singularity coming from the list of Namikawa-Ueno. And this is lying inside this 4-manifold. And then I also know that inside this manifold, the complement of this singularity is the 2-5 cusp. And let me now talk about this a little bit. What do we mean by 2-5 cusp? It is the zero set of this polynomial inside C2. And in fact, when you take the zero set and when you intersect that with the 3 sphere, it gives you 2-5 torus knot. And moreover, if you consider this S3 as the boundary of T4, and again, if you look at this intersection, then it is the ciphered surface of this 2-5 torus knot. And it is the result of Miller. But if you want to understand this cusp more topologically, then we look at its monodromy. And it is rather technical, but the monodromy is, it is mostly algebraic, in fact. The monodromy is given in this way. It is a word in the mapping class group of sigma 2. So let's look at this genus 2 surface. And on that, we have these standard simple closed curves, A1 up to A5. And when we say a word in the mapping class group, for instance, this A1 is a daintivist around this A1 curve. So basically, you cut your surface along A1, you rotate one end by 2 pi, and then you glue that back again. And such a word is the monodromy of our cusp. Then, by using that, and via some mapping class group relations, we show that this word is equal to 2 different words. And it is pure algebra, but geometrically, let me show you what is happening here. So we start with this cusp, this black curve, and out of it, we obtain 2 spheres. This is a sphere having 2 double points on it, and we get another one also. Again, it is a sphere having 2 double points. And this process is the first step here, is what we call deformation. From one cusp, we obtain this configuration. And then at these 4 double points, we are doing blow-ups. And then we obtain another configuration. These are all spheres. And moreover, this red curve, E13, it is the homology class. So it is a section of the vibration, and it is hitting these two spheres. And above, in fact, it was also hitting my other singularity. Let me show that. So if we look at this picture, here I have my section, and it also hits the other chain of spheres here. And so the existence of section is important for us. That is what I'm trying to say. And then we combine this configuration with the other two spheres. And we do blow-ups and some symplectic resolutions, some other operations. We combine them together, and we obtain such a plumbing diagram. Again, here each dot is a sphere, and they are transversely intersecting chain of spheres. And then to that plumbing, we consider the neighborhood of spheres, and to that we apply the generalized rational blowdown surgery. And so this is what we are doing. We take out those spheres and replace that by another 4-manifold. And it gives us a new manifold. We call it Y, and it is symplectic. Next, we show that Y is an exotic copy of CP2 blown up at 7 points. So to show exoticness, there is a kind of standard approach. It is computational. So first, we show that Y is homeomorphic to this standard 4-manifold. To show that they are homeomorphic, we do computations. We compute the topological invariance and fundamental group of our manifold. And then there is a theorem by Friedman. And by using his theorem, we conclude that they are topologically the same manifolds. And then next, we show that it is not diffeomorphic to that manifold. And to distinguish that structure, we use an invariant. It is called symplectic Kodaira dimension. It is a diffeomorphism invariant shown by Tianjunli. It is again computational. And this shows that we have such an exotic 4-manifold. And I will skip the definition of that invariant, but we can talk if you like. And on the same paper, let me state our other theorem. In that one, we were able to construct an exotic, again, CP2 blown up at 7 points, but this one is coming from a different vibration. So this is again a genus 2 vibration, but the singularities are of different types, type 5 and 5 star. And we also used the same operations. The proof is similar, but the pictures are different. And I want to show you one picture coming from here. So in this theorem, I have worked inside third degree Hirzebruch surface, F3, and I show the existence of such a pencil. And here C infinity, for instance, it is the +3 section of our Hirzebruch surface. And again, we have some irreducible curve. It is a member of a linear system, and we have some special intersection point. And then again, we proceed as in the previous case. By doing blow-ups, I reconstruct a singular fiber. This black part is a singularity on the Namikawa Ueno list. And here I'm giving a geometric construction of that. And then again, I work with this and its complement, and we proceed similarly, and we made our constructions. Let me pause here for a second. Do you have any questions up to now?
It seems no.
Okay. So this was the first part. Now let me start the second part. And here I will talk about exotic 4-manifold constructions again via genus 1 pencils. And again, I will introduce some notations. Let's say that you have a closed and simply connected and symplectic 4-manifold. And we have some numerical invariants of our manifold. C1 squared is the square root of its first Chern class. So it also satisfies this equality. 2 times Euler number plus 3 times signature of the manifold. And chi h is called the holomorphic Euler characteristic. So it is Euler number plus sigma over 4. These are 2 invariants. And then we have the geography chart. It is coming from complex surface theory, as I know. It is C1 squared and chi h coordinate system, let's say. And on the chart, we have some special lines. So we have the Noether line, and it is given by this equality, C1 squared equals 2 chi h minus 6. And there is also half Noether line, and it is C1 squared equals chi h minus 3. And in my work, I have made constructions lying between these 2 lines on the geography chart. And by the way, recall that for minimal complex surfaces of general type, the Noether inequality holds. So they are, if you have a minimal and complex surface of general type, then they are all lying above the Noether line. But for smooth and symplectic manifolds, it's not true. Below that line, you can have many interesting 4-manifolds. And let me show the picture. It is what we call the geography chart. And here I have half Noether line, and this is my Noether line. And again, my manifolds, I'm going to talk about them now. They are lying on this region, which means that the invariants of my manifolds are, staying in this region. And in my work, I have used another operation. These are called star surgeries. And these are due to Karakurt and Starkston. And these are new 4-dimensional symplectic operations. So remember, in the rational blowdown, we were working with only linear Plumbing diagrams. Now, in this case, we consider star-shaped Plumbing diagrams. I will show some pictures, but as an analogy, let's say. These are also symplectic operations. So you start with a star-shaped plumbing of symplectic 2-dimensional spheres lying inside a symplectic 4-manifold. And then you replace that with another 4-manifold. It is what we call convex symplectic filling. And its Euler characteristic is strictly smaller. So at the end of the day, when you do such an operation, you are getting smaller 4-manifolds. And later also Starkston showed that infinitely many star surgeries are not equivalent to any sequences of generalized symplectic rational blowdowns. Some types of star surgeries can be written as a sequence of blowdowns, but infinitely many of them cannot be written, so they are in fact different operations. Okay, now let me state my result. I showed that there exist simply connected and also symplectic 4-manifolds. They have exotic smooth structures, and some of my manifolds are lying on the Noether line, meaning that the invariants satisfy the Noether equality, and some others are lying between the Noether and half Noether lines. And in my work, I have used star surgeries, and I also used complex singularities. And also, in this work, I gave a geometric way of obtaining certain configurations of complex singularities in the rational elliptic surfaces. When we say rational elliptic surface, these are just complex projective plane blown up at 9 points. And in this part, I didn't use any monodromy arguments. In the literature, in general, people use mapping class group arguments. But here I just gave a geometric way of obtaining certain configurations. And briefly, let me give the proof idea. How much time do I have?
At least 15 minutes, actually.
Okay, great. Then I can.
We have started also a bit late, but you can also, I don't know, leave some time for questions. Yeah, go ahead, please.
Okay. First, again, let me give some notations and conventions. As I said, blow-ups and blow-downs can be done symplectically, thanks to Macduff. And again, I do all blow-ups in the symplectic category. And another notation that I should mention, the IN singular fibers. These are called necklace type singularities, for n is at least 2. And here again, each line is a 2-sphere. And self-intersections are all -2. By the way, when I say self-intersection, we consider the homology class of that sphere. It is an element of H2 of your manifold. And we consider the square of that class. It is what I mean. And these -2 spheres are arranged in a cycle. And this singularity is given by Kodaira. And another notation, E1. So we call this manifold CP2 blown up at 9 times E1. These are elliptic surfaces because they admit elliptic vibrations over S2. And En, these are coming from E1s. There is another operation. We call this fiber sum. And inductively, we produce such bigger manifolds. And then these ENs are Kähler, so they are both complex and also symplectic. And in my work, I have obtained configurations of those IN type singularities lying in the rational elliptic surfaces. And let me talk about some well-known facts here. So if you have a Jacobian rational elliptic surface, it is this 4-manifold, and it admits an elliptic vibration over CP1. And if it admits a section, then we call it Jacobian. And we have a cubic pencil. It is one-dimensional linear system of cubics, and it should have 9 base points by bezel. And when you start with a cubic, and when you blow up the base points of your pencil, it gives you a Jacobian rational elliptic surface. And as a result of blow-up, you get exceptional divisors, -1 spheres, and these are, they correspond exactly to the sections. And moreover, due to Miranda and Person, we know this result. They show that every Jacobian and rational elliptic surface is the blow-up of the base points of a cubic pencil. So they are all coming from certain cubic pencils. And if you drop the assumption of being Jacobian, then a rational elliptic surface is still a blow-up of CP2 at 9 points. But in this case, the blow-ups may not be necessarily at the base points. You may do blow-ups at other points. It is a difference, but in general, we work with Jacobian surfaces. Naruki, in fact, explicitly constructed configurations of singular fibers inside rational elliptic surfaces by blowing up cubic pencils. And then later Person gave the complete list of all singular fibers lying in the elliptic vibration zone R manifold E1. And in my work, I have made constructions coming from such pencils of cubics. And let me give a sketch of one of them. So it is just one pencil of cubics lying inside complex projective plane. And here C1 denotes a cubic, C is another one, and L is a line, Q is a conic, and their union is another member of that pencil. So their degree is 3 in total. And P and Q are the base points of that pencil, and their multiplicities are adding up to 9. And this configuration is lying inside the complex projective plane CP2. And next, I start with this pencil, and by doing blow-ups, and I did some certain operations, and out of it, I obtained this configuration. Here, the first one is I6 singularity, the second one is I3, and the last one is I2 singularity. And again, each line is a -2 sphere in this case. And first, I obtain these three lying inside E1, CP2 blown up at 9 points. And then I pass to larger and bigger manifolds, E-ends, by doing fiber sum operations. So from each E1, in fact, such a triple comes. And inside, for instance, in E5, we see 5 copies of such a triple. But I just work with 3 of them. And for my purposes, it was enough to consider 3 of them. And I took these 3 lying inside this manifold E5. And here the red curve is the -5 section of that manifold. And then out of this configuration, again, I did some certain symplectic operations. Out of this, I obtained this diagram. And this is one of the plumbings that we use in the star surgery. And this is a star-shaped plumbing. And it lies inside in this 4-manifold, E5 blown up at 3 times. And I obtained this configuration. And next to that plumbing, I applied star surgery. So we take this out, and then we replace that with its filling, V. And V is the symplectic filling. It is a symplectic 4-manifold. And it has the same boundary as our plumbing U. And we also know its topological invariance and stuff. And then I obtained such a manifold T. And next, I computed the properties of my manifold. So T is symplectic and simply connected. And it has an exotic smooth structure. And when I look at its invariance, I show that it is lying on the Noether line. And what else? And in my work, I also work with other configurations coming from different pencils. And then to those configurations, I applied different types of star surgeries. And then I have made other constructions. And those manifolds are lying below the Noether line. However, they are above the half Noether line. And here, one interesting question might be, can you get such kind of manifolds lying below the half Noether line? And there are certain conjectures. There are some open problems. And we don't know the answers to those conjectures. And it would be interesting to come up with such manifolds below the half Noether line, in fact. And I was going to mention another work, but I think it would be too much. So let me just stop here. Thanks for your patience, and let me know if there are any questions.
Thank you, Sümeyra.
You're welcome.
Very much for this nice talk. Any questions? For the moment, I also stop recording to also encourage maybe dummy questions.